The science case for Argos is something that's familiar to all of you. This is more of a review slide than anything. People understand here that aerosols are very important for the energy balance of the climate system. We need to know where they are and where they are going. The focus here is on stratospheric aerosols, where we have a natural background component, we have transport from anthropogenic sources in the troposphere, and we also have impulsive injections, the large volcanic eruptions and pyrocumulonimbus events that we've been hearing about. Stratospheric aerosols can also cause cooling, which will offset warming from greenhouse gases. This is an important topic because you hear a lot of people talking about the ideas of geoengineering projects, and so we would like to be able to know what is happening if somebody wants to try a project like that. So we need satellite measurements to do this, ideally. We'd like to have good temporal sampling to take care of the transport. We'd like to have spatial sampling to know where things are, and vertical resolution to know where the material is so that we know where it's going to be transported. And we're using limb scattering measurements here to do this. Very simple cartoon of the Argos concept. Argos will be on a satellite. The satellite will point in the nadir. Okay? All right. Maybe now I won't have to talk so loud. If I overdo it, remind me. So we have a satellite that the body points in the nadir. We have 8 apertures. I'll show you some better pictures of that in just a minute, that look out towards the limb, forwards and backwards along the orbit track, perpendicular to the orbit, and then at 45 degrees angles between each of those apertures. The slits cover 0 to 60 kilometers on the Earth's limb. We're not a scanning instrument, it's just a fixed aperture. And we'll be flying at about 550 kilometers altitude. Here's a little better diagram that we have now with the instrument. What we've done is start from the ALTIUS limb profiler design. You'll hear about ALTIUS from Glenn Jarosz in the next talk, and focused on making aerosol measurements in a compact package. The schematic that you see up there at the top, this is a fairly small instrument. It's 20 centimeters across, so it's about the size of my hand, pointing outwards. 4 kilograms in mass. We've used bandpass filters at near IR wavelengths to get better vertical coverage, altitude coverage, for the aerosol. So we've chosen wavelengths at 870 nanometers and 1550. 870 has heritage with current ALTIUS measurements. 1550 has heritage with SAGE. And the separation between these should be enough to help give us information about particle size. We've added a forward view for better aerosol sensitivity in the southern hemisphere. I'll show you a discussion of that in a moment. We've added cross-track views, which give us improved spatial coverage, and I'll show you that this actually will give us information about short-term variations in aerosols. And we're flying a technology demonstration next year with what's called a hosted payload provider, and this gives us better margins for size and mass compared to a CubeSat. Point to mention here is that we are using a commercial camera for this to save money. So I mentioned the sensitivity. The ALTIUS limb profiler has, let's see if I can get the laser here. I think that's the laser. Okay, so the ALTIUS limb profiler looks backwards out of the satellite, and that means that its scattering angles are very high in the southern hemisphere, and very low in the northern hemisphere. The red and blue colors show you June and December measurements, and having high scattering angles means that you're down here in a typical phase function curve. There are a couple different examples on here. It doesn't matter which one is which. Well, what we've chosen to do with Argos is to make an additional measurement in the forward direction. We'll sample the same air mass within about 15 minutes using both forward and backward views. And so at a middle southern latitude, we'll get points here and here. And that will give us leverage to help potentially discriminate between these phase functions, because you can see that there's a difference down here. What also simply will give us more sensitivity in the south. We've also added these cross-track views, and the cross-track views are very nice because we get a lot of sampling out of it. This is a little simple cartoon showing you just 15 minutes of time during one orbit. Each of the apertures is shown in a different color, and because of this combination of forward and backward in views, in 15 minutes we view from 65 degrees south to 40 degrees north. What that also lets us do, and this is a bit of a busy plot, but thank you. Yes, it is busy. But it does try to show you something that it turns out to be very useful for us. The red dots show you the positions of all the Argos samples for a given orbit. The green shows you the measurements from the preceding orbit. And you can see here that the cross-track views from the preceding orbit actually run right along the path of the forward and backward views from this orbit N. Meanwhile, from the following orbit, the cross-track views in the other direction also fall across that path. So we'll get measurements, particularly at the equator where things overlap nicely, we'll get measurements from 3 consecutive orbits over essentially the same air mass. We've also looked at what the spatial sampling will do to help us for understanding geophysical behavior. This is some work that Pete Calarco has done. A couple years ago, we took output from the GEOS-5 atmospheric model and sampled the optical depth from that after a volcanic eruption using both the typical OMP sampling, simply a long track, and then adding in the additional cross-track measurements that you get with an Argos. And you see that the uncertainty in total optical depth, around after the eruption reaches as much as 15% with just a long orbit sampling. But if we add the additional sampling from Argos, we reduce that to about 3 or 4%. Other thing that Pete's done recently is to look at the sampling that you get in GeoCCM if you had only Argos, if you had only long track views or Argos views after a particular volcanic eruption. You see, with just a single view, you get 1 pixel here, but you don't, I think the boxes are maybe 1 by 1 degree. But you don't get a lot of other information. If you take all of the Argos views, you now really show the structure of this much more clearly. Okay, so let me just describe the instrument briefly. I mentioned we have this commercial camera here. We've actually modified the commercial camera to take off some of the housing, and that's done to get the slit plate here very close to the focal plane. Light comes in through each of the apertures here. We have short pass and long pass filters to help limit the light to just the wavelengths that we want. Lenses here focus on the central mirror. This is an 8-sided mirror. I'll show you an example of the real one at the end of the talk. That directs the light onto the focal plane, and then we get all of the light simultaneously on the focal plane. This is a different cartoon of the viewing geometry. In each of those circular apertures that you see, we have 2 slits, one for 870 nanometers and one for 1550. The slits are pointed about 1 degree apart, which separates them by about 40 kilometers on the limb. The slit height is 1.3 degrees to give us altitude coverage from 0 to 60. Part of our need to have that higher altitude coverage is because the Earth is oblate, and so the pointing of the spacecraft on the limb will vary as we move through the orbit, so we need a little extra room to make sure we cover the stratosphere. We built a predecessor instrument. I'll show you that in just a moment as well, but we took that predecessor instrument and operated it up on the roof of NASA Goddard. This is actually the instrument itself, looking out towards the side. This instrument had just horizontal pointing apertures, not angled downwards. But you can see the pattern of the different slits on the focal plane, which is what we'll actually get on orbit. This instrument has a good history of support from both NASA and Goddard itself. I'll mention the Earth Science Technology Office in just a moment. We started out with internal funding in 2016 and literally went to the store and bought parts for this version of the instrument. Developed the second instrument with funding from ESTO for what they call Instrument Incubator Program in 2018. You can see this version looks like it's sitting up on a little pedestal. It's one of the changes that we made going to the new instrument is that we were able to bring the focal plane and the slit plate very close together and remove a lot of complicated optics in there. We did get funding to take this instrument and try to fly it on a balloon. That was supposed to happen in 2020. That was not a good year to try to be doing a field campaign, obviously. We did get an extension to try to make that happen in 2021. Had a problem with the instrument power supply basically the day before we were going to ship for the balloon flight. And so unfortunately, we did not get to try that. We're still hoping to get an opportunity to fly that one. But at about that same time, we got funding from ESTO for the INVEST program, which is what we're working under now. And that instrument is scheduled to fly in 2024. The INVEST is a NASA program called In-Space Validation of Earth Science Technologies. Through 2017, this program was focused on doing CubeSats as the flight model. Oops, that was supposed to be a less than. I wish it was. I wish it was a greater than, but it's not. It's a competed program through what NASA calls ROSES. You have a limited funding and a fairly tight schedule, and so that does limit what you can do with the program. What we were able to do in the 2020 edition of this program was to also work with a hosted payload provider, and that's made life a lot better for us in terms of work that we have to do for the instrument. Just got a couple pictures, actually I'll just skip through. I'll just mention this quickly. We've taken an early version of the camera and done testing with it already. Done vibration testing and thermal vacuum testing with our baseline camera to be sure that we're going to get the kind of performance that we're looking for. I mentioned this hosted payload concept. So Loft Orbital is one company that does this. There are other ones that do it. But we will be flying on a bus that they are setting up, which is a variant of the Airbus OneWeb Aerobus, which is, they have, I think, 300, 400 on orbit. So that basic design is very well proven. Loft offers this configurable package for you, because they call it the Payload Hub, which provides electrical and mechanical and thermal support. You have good margins available for size, mass, and power. And so we did not have to modify our instrument design really in any way to work with this. We will be one payload out of a couple on the overall mission. We don't know who the other partners are yet. They will let us know that at some late date. But they will provide the onboard data storage and processing, commanding, communications to the ground, and there are frequent options for flight, and on the order of quarterly. And so it's a very flexible way to get an instrument ready to go. And this is actually my last slide, just showing you that we do have real hardware now. This is the central hub for the instrument that will have all those apertures coming out. This is an example of one of the prisms, the central mirrors. I keep using the term prism. Central mirrors. This is now one of the apertures with the baffles that we've designed that will help reduce stray light. We have all of these parts in-house. We are starting to do the integration. We'll be doing environmental testing this fall, deliver the instrument in September, and the target for flight will be sometime in spring 2024. And while this is formally a technology validation mission, we do want to generate science products, and we're actually working with Ghassan Taha to adapt the current OMPS aerosol algorithm to do our retrievals. And that's it. Thank you.